The topic for today's seminar is implant design. These are the contents under which it will be covered. Introduction. Implants are designed with so many intricate features, and it is important to understand the biomechanical rationale and their clinical significance. An implant system can represent a specific concept, inventor, or patent. It consists of necessary parts and instruments to complete the implant placement and its abutment components. Definitions. An implant is defined as an alloplastic material or device that is surgically placed into the oral tissue, beneath the mucosal or periosteal layer, or within the bone for functional, therapeutic, or aesthetic purposes. Implant system. Dental implant components that are designed to mate together. An implant system can represent a specific concept, inventor, or patent. It consists of necessary parts and instruments to complete the implant body placement and its abutment components. As seen in the previous seminars, implant can be classified depending on the placement within the tissues, depending on surface texture and cross-section, depending on the materials used, on the reaction with bone, and on the treatment options. Depending on the placement within the tissues, they can be endosteal, subperiosteal, transosteal, intramucosal, or fibrointegration implants. Endosteal dental implants. These could be blade or plate implants, which are useful when the ridge is thin, wherein tricortical anchorage is the most suitable technique. Ramus frame. It's a horseshoe shaped and it is inserted into the mandible. Root form implants. They are the gold standard to replace missing teeth. They could be further classified into screw or thread type. This uses threads for primary stabilization. Or cylindrical or press fit type, which uses friction for primary stabilization. Subperiosteal implants. These are placed beneath the periosteum that overlies the cortex. Much of the support is provided by the gums. They may be unilateral, complete, or circumferential. Transosteal implants. They are a combination of both endosteal components and those of subperiosteal. These implants penetrate the two cortical plates. Intramucosal dental implants are inserted directly into the oral mucosa. In this case, the mucosa is used as a site of attachment, and the metal inserts are usually made from titanium. Fibrointegration implants. The implanted tooth is completely encapsulated by soft tissues in the mouth. Depending on surface texture and cross-section, they could be cylindrical implants, which can be conical, straight, or tapered, and is tapped or pushed into the bone site that has been prepared. Next are the threaded dental implants. Threads increases the implant surface area, providing a more solid contact with the jaw. Hollow dental implants, as the name suggests, they have hollow design in the apical portion. The perforations on the implant sides are arranged systematically. Vented dental implants, there is a vertical groove that connects to the apical veins. Implant design can be described under macrogeometry and microgeometry. Macrogeometry refers to the overall shape designed to optimize precise placement, initial stability within the bone, and distribution of forces within the bone. Microgeometry refers to the surface structure or degree of surface roughness of the dental implant. Implant macrogeometry can be studied under the crest module, body, and apex of the implant. Now, the crest module refers to the neck portion of the implant. It is the portion of the implant that engages the crest of the bone and is designed to accept the prosthetic component. If the crestal module is designed to be placed flush with the bone, it is called bone level implant. And if the crestal module is designed to extrude 2 to 3 mm above the bone, it is called tissue level implant. The occlusal surface of the crestal module has a platform on which the abutment sits. The implant abutment connection in the crestal module has the anti-rotational component that can hold the abutment and prevent it from rotating. This connection may either be within the implant body, then it is the internal connection or internal hex, or outside the implant body, then it's the external connection or external hex. Crest module can be described based on these features, that is collar design, collar shape, collar size, surface, and presence of microthreads on the collar. Collar design. Based on this, it can be classified as straight or parallel sided. This is the most common collar design. Divergent or flared collar. It reduces the least amount of stress on the crestal bone and is more biologically compatible. This is probably due to increased surface area. Convergent or tapered, this design has favorable stress distribution. Next is the collar shape, which may be scalloped or straight. In the scallop design, follows the three-dimensional contours of the bone. The idea of the design is to preserve interproximal bone and to avoid black triangle embrasures between the restorations. The scallop soft tissue apposition area allows for the development of biologic width around the entire neck of the implant. Now the straight design, the stress distribution pattern in this design is static, meaning it does not increase or decrease the force distribution in the crestal area. Studies have shown that parallel crestal module design produce a lot of shear stress in the crestal region, thereby causing more bone loss. Collar size. The crestal module is designed to have slightly larger diameter than that of the body of the implant. The advantage of this is that it improves the initial stability of the implant, decreases the stress concentration, and prevents the entry of bacteria and fibrous tissue by sealing the site of osteotomy. Collar surface. The crestal module may have either a smooth or polished collar or a rough or non-polished collar. The earlier concept was to have a smooth collar. The earlier concept was to have a smooth collar so that cleaning and maintenance were easy. However, smooth collars produce greater shear force due to low surface area. This led to frequent marginal bone loss. And therefore, rough surface crestal modules have become more common. Microthreads. These are small grooves that are placed on the crestal module to improve the surface area of the bone implant interface near the crest. They help in maintaining the crestal bone height by dissipating the occlusal loads. The implant abutment connection, it is a junction between the dental implant and its abutment. It is one of the critical determinants of the strength and stability of an implant supported restoration and has a major role to play in the success of the implant. They could be internal connection or external connection. External connection, the crestal module of the implant has a component which fits in the component present in the abutment. Whereas in the internal connection, the connector projects from the surface of the abutment and fits into a depression on the surface of the implant. Internal connection could be passive fit, where there's a mild space between the components, or friction fit, as in Morse taper. Morse taper was developed by Stephen Morse in 1864. It's an internal joint design between two conical structures. The internally tapered design creates significant friction via high propensity of parallelism between the two structures within the joint space. Platform shifting involves the use of an abutment that is smaller in diameter than the implant platform it is attached to. The abutment diameter is smaller than the implant crest module. This moves the implant abutment junction away from the outer margin of the implant. Moving the margin inwards moves the bacteria more internally. Therefore, the bacteria are moved away from the bone crest, reducing the crestal bone loss. Body of the implant, it is the part between the crestal module and the apex. The body of the implant can be described based on the taper, thread design, and other special features. Taper refers to the parallelism between the walls of the implant. There could be three forms: cylindrical implants, where the implant body diameter is constant from the crest to the apex; root form implant, where the implant body diameter remains constant from the crest to the middle third, and it tapers in the apical third just like a natural tooth; or pio implant, where the implant is custom milled according to the shape of the extraction socket. Macrogeometry of implant body. The implant body can be threaded or non-threaded. Threads are designed to maximize the initial contact, enhance the surface area, facilitate the dissipation of loads at the bone implant interface. The functional surface area per unit length of the implant body is also modified. Threaded implants can be described based on the thread shape, thread pitch, thread depth, thread width, and the thread diameter. Thread shape, the threads could be V-shaped, buttress-shaped, reverse buttress, or square-shaped. V-shaped threads are strong, but they transmit more shear forces to the surrounding bone. Square thread forms transmit occlusal forces with less shear force than V threads. Buttress threads minimize shear forces in a manner similar to square threads, and they combine excellent primary stability with the best features of both V and square thread forms. Thread pitch, it is the distance from the center of the thread to the center of the next thread. This is measured parallel to the axis of the screw. Maximum effective stress decreases with the decrease in pitch. Thread depth is the distance from the tip of the thread to the body of the implant. Outer diameter is measured from the maximum width of the thread, and the inner diameter measured from the width of the implant between the threads. Greater the thread depth, greater the surface area of the implant. Thread depth is most in the V-shaped threads. As the diameter increases, the thread depth also increases. Coming to implant length and diameter, implant length is the dimension from the platform to the apex of the implant. Implant length varies from 6 to 20 millimeters. Implant width, or the diameter of the implant, is measured from the widest point of a thread to the opposite point on the implant and typically ranges from 3 to 7 mm. Increase in the implant diameter increases the functional surface area of the implant. An increase in 1 mm diameter of the implant increases the functional surface area by about 33%. Apex of the implant, it is of two types, self-cutting apex and non-self-cutting apex. Anti-rotational features that are present in the apex are the screw vents, slots, and the grooves.
Coming to the implant microgeometry, which refers to the surface structure or the degree of surface roughness of a dental implant. Wenberg has classified implant surfaces based on the surface roughness as smooth, which is less than 0.5 micrometer, minimally rough, which is 0.5 to 1 micrometer, intermediately rough, which is 1 to 2 micrometer, and rough, which is 2 to 3 micrometer. In general, it is moderately rough, which gives the best result. Based on the texture obtained, it can be concave and convex based on the mechanical and chemical modifications on the implant. And based on the orientation of the irregularities, it can be isotropic, which has the same topography independent of the measuring direction, and anisotropic, where there's a clear direction but different considerably in the surface roughness. Now, the implant macro design of the surface condition especially has a great impact on the dynamics of osseointegration. Implant surface modifications have been used to improve the quality and quantity of the bone to implant interface. The secondary stability depends mainly on the implant surface. There are differences among the surfaces of the available dental implants are the roughness, chemical compositions, surface roughness, existence of impurities resulting from the manufacture or handling, the type of the oxide layer, the crystal, and the oxide thickness of the oxide layer. This is important since the proteins interact with the oxides of the implant surface, and interaction depends on these parameters. The traditional unmodified implant surfaces lack the full capacity to consistently achieve osseointegration and combat biofilm formation. Clinical evidences suggest that local dissolution of products and particles released as a result of implant surface degradation can trigger pro-inflammatory responses. There has been a growing demand for implant with a better surface texture and better osseointegration, and therefore topography of an implant can now be manipulated at a wide range of scales. In conquering these hurdles, a diversity of physical, chemical, and biological modifications have been applied to implant surface. The physical modifications can be at micro level and nano level. In the micro level, an increase in the implant surface area on the micrometer scale enhances the fibrin matrix formation as the osteoconductive scaffold for the osteogenic cells. The changes here range from 1 to 100 micrometer, and it includes machining, grit blasting, sandblasting, and acid etching. At the nano level modification, this increases the implant surface roughness and wettability, as well as the free surface energy to enhance the cell growth. Here the changes range from 1 to 100 nanometer, and it includes laser ablation and nano composites. Several chemical modifications have been performed on implant surface to improve osseointegration and mitigate the biofilm by providing a hydrophilic surface. And currently used methods are acid etching, alkaline etching, crystalline deposition, and anodic oxidation, UV treatment, plasma oxidation, fluoride treatment. Biological modifications are also used, which affect the osseointegration and biofilm formation, which are the platelet-rich plasma, extracellular matrix, peptides, growth factors, and drugs. Now, turned surfaces, also known as machined or smooth. Now, implants with turned, milled, or polished are considered the first generation implants, which were used in the 1990s. They appear smooth to the naked eye. Slight grooves and ridges are created during manufacturing, which is seen under SEM. And for this reason, the term smooth should be avoided. It has an average roughness of 0.96 micrometer. It is the bone fixation of a firm bone fixation is achieved when the surface roughness ranges from 1 to 1.5 micrometer. Therefore, modifications were proposed to change the characteristics of the surface from turn to roughen to improve the stabilization of the implants and to increase the surface area. So various methods were followed, like chemical and mechanical, which can further be classified into additive processes and subtractive processes. The additive processes and the subtractive processes are listed as follows. Coming to grit blasting. So it's a process by which the metal surfaces are textured with a pressurized spray to increase the irregularity of the surface of the implant. Sandblasting the metal core with gritting agents is done. Alumina, titanium oxide, and zirconium oxide are the blasting materials which are used, and the blasting material should be stable, biocompatible, and not hamper osseointegration. The titanium oxide of 25 to 50 micrometer are projected with high velocity towards the implant surfaces. In a 10-year follow-up study, titanium dioxide grit blasted implants showed 96.9% survival rate and showed a better prognosis than those with relatively smooth machined implants. The advantages of grit blasting are it increases the surface roughness and promote osteoblastic activity and get a faster, stronger level of osseointegration. It also allows adhesion, proliferation, differentiation, and matrix synthesis of osteoblasts and chondrocytes. The limitation is the possibility of contamination of the surface. Coming to acid etch surfaces, so here it's a process that removes small amount of materials to create pits on the implant surfaces. Chemicals such as hydrofluoric acid, sulfuric acid, nitric acid, and hydrofluoric acid are used. So it was proposed to modify the implant surfaces without leaving any residue, which was found after sandblasting. And to avoid non-uniform treatment of the surface, acid etching creates micropit which are from 0.5 to 2 micrometer in diameter. And Coleret et al. Compared the etched HCl and H2SO4 and found a resistance to torque removal to be 4 times greater for the acid etch implant as compared to the machine implants. Coming to dual acid etch surfaces, it has been proposed to produce the microtexture. It enhances osteoconductive process, and the success rate was evaluated for this implants at 36 months was 95% as compared to 86% for machined implants. The advantages are that the microscopic increases in the surface area is attracted to the osteoblast activity, and there is a resultant increase in the mechanical locking of the implant bone. Coming to sandblasted and acid etched surfaces, So sandblasting with large grid particles of 250 to 500 micrometer are done. Subsequently, etching is done with an acid to create the micro irregularities with strong acids. Now these removes the contaminants and pits and craters are formed, and therefore there's a homogeneous irregularities are formed. Here it increases the surface area and bioadhesion. Long-term survival rates of SLA implants are 99.2%. Here, the surface roughness was as low as 0.2 micrometer, and the application of a secondary modifying approach inhibits the bacterial colonization while preserving the surface roughness. The advantages are it improves the bioadhesion, accelerates osteoblast attachment and retention, facilitates osteointegration, bone apposition, and increases the bone anchorage. Coming to alkaline etching, this does not alter the surface roughness, but it affects the surface charge. Uh, Sodium hydroxide is used and a negatively charged surface rapidly absorbs calcium ions, and there is initial calcium ion is quickly followed by deposition of phosphate ion. Coming to laser surface.
Laser surface.
Coming to laser surface modifications, laser ablation is a process to create nanoscale channels around the implant collar area. This is complex, precise, and a high resolution geometry is generated. Here, the connective tissue they run perpendicular to the implant surface, and the laser ablated as compared to the parallel orientation of the fibers around the implant surface. Such as in laser lock implants, there are three zones. The upper zone is with a machined surface, and the middle zone consists of 8 mm microchannels, and the lower zone consists of 12 mm microchannels. Now, these microchannels were engineered to establish a supracrestal uh, connective tissue attachment to the implant that might preserve apical migration of the junctional epithelium. The advantage of this is it induces significant or more bone to implant contact, large torque removal values compared to the machined surfaces, encourages attachment of connective tissue and bone. There is lower biofilm formation as compared to machine and grid plastered surfaces, and it's an ideal design for immediate placement post extraction. Coming to plasma spraying, it's a technique in which the hydroxyapatite ceramic particles are injected into the plasma torch at high temperatures. So the plasma flame with the hydroxyapatite particles are heated approximately to 15,000 Kelvin and then sprayed on the titanium implant surface. Now, modifications further can be done by changing the spraying parameters such as the gas combination, the spray flow rate, the power, and a hydroxyapatite layer of 40 to 50 micrometers can be formed. The advantage is it is relatively inexpensive. The mechanical properties of the metallic substrate are not compromised during the coating process. The limitations could be it forms a mechanical bonding only with the metallic implant surface, and there can be sources of contaminations from the nozzle of the sprayer. Coming to anodic oxidation, it's a process that modifies the titanium surface by electrochemical methods to create a thicker titanium oxide layer. The titanium oxide layer which is present is 17 to 200 nanometer thick, and by anodic oxidation we can take it to 600 to 1000 nanometer. The anodic surface is the micro nanoporous surface which is produced by potentiostatic or galvanostatic anodization in the titanium in strong acids. Its advantages is it encourages gingival fibroblast deposition, adhesion proliferation, improves the bone to implant contact, and reduces the bacterial adhesion by 1 to 2 logs. Coming to discrete crystalline deposition, it is a sol gel process where a double acid edge surface is modified with calcium phosphate particles of 20 to 100 nanometer, and after this process 50% of the surface is composed of the calcium phosphate particles. It's seen in the nanotite implant by Biomet, which has a 1-year success survival rate of 99.4% as compared to machined and acid edge implants. Discrete crystalline deposit has shown significant reduction in the bacterial attachment. Its advantages is it has a better osseointegration, displays increased bone to implant contact in the animal models due to enhancement in the surface nanotopography. Coming to UV treatment and photolization, UVA and UVC waves can increase the hydrophilicity of the titanium surface and enhance the osteogenic cell attachment and proliferation. Its advantages are it promotes bone formation in the early phase of osseointegration and also shows an antibacterial effect. Coming to ion sputtering coating. So sputtering is a process by which in a vacuum chamber, the atoms or the molecules of a material are ejected from a target by bombardment in a high energy ion. Coming to various dental implant coatings are present such as hydroxyapatite, nanocomposites, magnesium, graphene, growth factors, extracellular matrix, peptides, antibiotics, and polysaccharides. So hydroxyapatite coating, its advantages are there is an acceleration of the early healing and the ability to bond to the bone. It readily absorbs the protein onto its surface, and this could increase the binding of the fibrinogen. In turn, can result in an increased platelet adhesion and activation. The fibrin binding to the implant surfaces can serve as a bridge. Now, this can be achieved by a plasma spraying, functionally graded coating, laser ablation technique, and pulse laser deposition. Now, the clinical advantages of this are it increases the surface area, increases the roughness of the initial stability. There is a strong bone implant interface. Additional advantages of hydroxyapatite over titanium plasma spray include faster healing of the bone, increased gap healing between the bone and the hydroxyapatite, stronger interface than the titanium plasma spray, and less corrosion of metal. Disadvantages of the coating include flaking, cracking, or scaling on insertion, increased plaque retention, increased bacteriitis for infection, complications of treatment of failing implants, and increased cost. Now, nanocomposites, various nanoparticles are added through nanoparticle compaction, plasma spraying, physical vapor, and hot isostatic pressing. The various available nanoparticles are titanium dioxide, silver, hydroxyapatite, pectin, carbon nanotube, can be added to titanium using both physical and chemical techniques. Nanocomposite allows the detachment of adsorbed salivary proteins and adherent bacteria under shear forces. The silver nanoparticles have shown statistically significant antibacterial effects. It improves the biocompatibility and osseointegration and reduces the biofilm formation. The possible disadvantage could be the proper fixing of the particle should happen to the surface, which is a high safety concern. Biological methods, various biological agents such as platelet-rich plasma and platelet-rich fibrin are used to enhance the bone healing and formation. Peptides such as P15, bactericidal sclerotin promote osseointegration and improve the bone implant implant ratio. The growth factors such as the bone morphogenic proteins, platelet-derived growth factors, fibroblasts have accelerated the tissue healing, and drugs such as statins, bisphosphonates, and antimicrobials are also used as coating, which provide which enhances the bone healing and formation. So various implant systems have various surface coatings which are available. Such as Strawman has the SLA surface, the Noble BioK has the T-Unite surface, and BioHorizon has the laser lock, and TI has the nanotite and the titanium plasma sprayed surfaces. In Ostem, we have the SA, which is a sandblasted acid edge surface, which has the surface roughness of 2.5 to 3 micrometer approximately, which has micro pits of 1.3 micrometer. In the CA form, there is the super hydrophilic assay, which is encapsulated in a calcium chloride solution. In the BA form, it's a low crystalline nanohydroxyapatite, which has a surface roughness of 2.5 to 3 micrometer. And in the HA is the high crystalline hydroxyapatite, which has a surface area of surface roughness of 30 to 60 micrometer.
These are my references. Thank you.